What I want to discuss are some general problems in Hamiltonian PDE, which I think are challenges, if you want, in PDE, but perhaps mainly challenges in analysis and provide us a source of good questions to think about. Now, because it's a rather short lecture, I will not, to save time, I will not mention names, or rarely mention names, which will avoid to being complete in whatever the credits I'm giving to various people, and also not much background material. There will be, as I understand, a written text, and then that can really make up for these shortcomings. So, it's difficult to give a talk completely on the philosophical level. So what I will do are project transparencies, which may look a little bit on the technical side, but the comments I will make will be more of philosophical, at a more philosophical level, and will give some general ideas of where the thing go to and what they are related to. So it is a rather vast area, and I'm sure Sergio Kleinerman in his talk will cover some other aspects of this general direction. What I want to discuss are, at least briefly discuss, because each of these topics is in a sense a whole area by itself, are questions which are related to the Cauchy problem. So existence of global solutions, questions related to blow-up behavior, and then also questions about the general dynamics in phase space, like growth of Sobolev norms, existence of invariant measures, and Km tori. About the last topic, I would perhaps disagree with what Yasha Sinai was mentioning in his talk, is that essentially Km did what it was supposed to do, so we should look for something else. I agree for certain periods of time not much happened in that field, but it doesn't mean that necessarily this ideology is dead and that one should forget about it. So in any case, there are two model equations. The first is the nonlinear wave equation, and the other one is the nonlinear Schrödinger equation. These equations, of course, they have been extensively studied, perhaps more than any other kind, and they have a certain physical interest. But for me, what is mainly significant about it is that they represent perhaps the simplest model cases. The first one, in the form it is written there, represents a situation where you have finite speed propagation, and the other one, infinite speed propagation. No, I mean, if you have, basically it means that if you look at a later, say a short later time, what happens in the bounded region, or on a small interval, how much it can be localized, how much this time evolution really can be localized in space, and that is considerably easier in the case of the wave equation than in the case of the Schrödinger equation. Now, on the philosophical level, that difference has certain effects in the sense that, for instance, the Cauchy problem is easier, generally speaking, perhaps to study for the nonlinear wave equation than for the nonlinear Schrödinger equation. On the other hand, it is not like that in any problem you have an advantage there, and the fact that there are more separations, say if you are in the setting of bounded domains, so you don't look on the line or in Rn, but you look what happens on a bounded domain, because of more separation properties in the, say, the frequencies for the nonlinear Schrödinger equation, say for the linear Schrödinger equation, if you look at the nonlinear Schrödinger equation, you will have more what you may call some kind of Nekorotchev type stability effects, and also, say, if you study Km tori, it is easier to study them in the case of the Schrödinger equation than in the wave equation, for instance. So you do not have always a disadvantage because of this different dispersion for Schrödinger equation. Now, another comment on the philosophical level about research in the next millennium, perhaps, is that there are, of course, many problems we cannot solve, and we like to get an intuition. Now, how do we get an intuition? Well, essentially what I understand is that presently the only kind of numerical simulations you can make are cases of radial data. There is nothing wrong with that, but it would be very good to have some kind of reliable numerical experiments. What you may call some kind of certified numerics, and this is greatly missing. I hope at some stage I will also show you certain cases where not only the numerics can give an intuition, but in fact can solve the whole problem. It will not give too much insight, but I mean, we get used to that. So, yeah, as I said, the slides are perhaps more technical than I should have done it, but still you have to be concrete about the objects you're talking about. So what they said is that these two guys are Hamiltonian equations. Is of course well known. The first case, the canonical coordinates are the position and the speed. You have a Hamiltonian H. In the case of the nonlinear Schrödinger equation, like was already mentioned in Jörg's talk, Jörg-Fröhlich's talk, the canonical coordinates are the real and imaginary part of U. So in the first case, y and v are real functions. In the second case, it's essential to look at U as a complex function. Now, the main reason I wanted to put this transparency there, even if you are not willing to read it in detail, what you should observe is that there are two signs there. There is a plus sign. You have a plus sign which, in the case of the wave equation, also gives you the plus sign here, a minus sign for Schrödinger, which gives you a plus sign here, and alternatively. So this is quite important, because you see, if you have, for instance, in the case of the Schrödinger equation, the minus sign here, the plus sign there gives you a Hamiltonian which is bounded from below. So the conservation of the Hamiltonian gives you immediately at least gives you one conserved quantity, which is responsible for a bound on the H1 norm in the case of a classical data. So the general philosophy, for instance, in the Schrödinger case, is that if you have, say, classical smooth data, in the defocusing case, which corresponds to the good sign, the plus sign, that these solutions will go on for all time and will remain smooth, that there is no singularity formation, although, well, I mean, I believe Sergio Kleinerman may have a different opinion about that, and that there could be conceivably a breakdown of singularity. So, I mean, this is something which is a bit on the philosophical level, and where definitely experiments would be interesting, because already in the radial case, this is not well understood. Yeah, of course, yeah. And then the minus sign, well, in a minus sign, your Hamiltonian is not necessarily bounded from below, and it is well known that for a sufficiently high nonlinearity, even classical solutions can develop singularities, and it is a most interesting area of research. What is the nature of formation of the singularity, what are the stability properties, etc., where there has been, I will come back on that, there has been quite a bit written on that, but unfortunately not too much of that is really mathematically rigorous, and it's definitely a source, a very good source for problems. So since I decided to be a bit on the more technical side, let's continue in this bad direction. And I think it's less tiring just to project you the whole transparency and start moving around pieces of paper there. You see, there is one important distinction, which is the case of an H1 subcritical model. H1 subcritical model means that basically H1 is more than enough at least to solve the problem locally. So if we discuss the Schrödinger case, for instance, then that is okay in dimension 1 and 2, no matter what is the nonlinearity. And then in dimension 3 and larger, you have to put some bounds on the nonlinearity. So in particular, you have classical solutions which will be global. We are talking about the defocusing case, of course. As long, of course, as this smoothness of the initial data is compatible, say the The smoothness of the nonlinearity should be, of course, compatible with the smoothness of the data you're dealing with. So we have here a power p. When the p is too small, you have a lack of smoothness of the nonlinearity, so that can create a problem, and I will not discuss that. So in any case, this is reasonably well understood, and we get global classical solutions. Now, what is less understood is the H1 critical case. Now, the H1 critical case corresponds with, so for instance, if I take d equals 3, then I would have for Schrödinger u at the power 4. For the wave equation will be y at the power 5th. So in that situation, the homogeneous H1 space is the scale invariant space for the equation. You have local well-posedness. You have local solutions in H1, but unfortunately the time interval does not only depend on the size of this H1 norm, which you have a priori under control from the Hamiltonian, but also on the concentration. So basically, the trouble in that situation is that you have to avoid concentrations of energies on small balls. And that is an issue which has been studied both for the nonlinear wave equation and the nonlinear Schrödinger equation. In the case of the nonlinear wave equation, these are results which go back to the 80s, the late 80s. One knows that there are global classical solutions as soon as S is at least equal to 1, and moreover there is scattering. We're talking about the defocusing case. In the case of the nonlinear Schrödinger equation, this is not known, and this is in fact only quite recently understood in the radial case. This is a typical issue where there is a problem of finite speed, of possibly infinite speed propagation, is that it's much harder for Schrödinger to keep track of where these possible energy accumulations occur than in the case of the wave equation. Now, what is interesting is that in the supercritical case, so in the supercritical case, H1 supercritical case, to study the problem locally, what you need is more smoothness than provided by H1. So in that case, there is an extra difficulty, and the extra difficulty is simply that we do not have at our disposal conserved quantities which go beyond H1. Except, of course, in the integrable models. But in the generic situation, say, if you need H2 to solve the problem locally, well, okay, fine, start from a C-infinity data, whatever, from a very smooth data, what is going to happen when time goes on? Do you have any kind of control on this H2? So there is a possible breakdown of smoothness there when time goes on. And again, it would be most interesting to have reliable computer experiments of what happens there. What I understood from the people who have done experiments, of course only with radial data, it's already open for radial data in the supercritical case, is that all the evidence is, say in the defocusing supercritical case, that the higher the nonlinearity, for instance with the wave equation, the higher the nonlinearity is here, we are talking about the plus sign here or the minus sign here, the higher the nonlinearity, the faster this scattering occurs. Now, on the philosophical level, I mentioned to you that numerical experiments are interesting. The truth is that such a theorem, if you think about it, in fact could be proven. If I give you any classical data and you believe that there will be scattering after some time, well, this can be proven by computer. It's not only that you can see it. Well, it means that asymptotically the evolution will be like the linear. And, well, it's enough to follow that solution sufficiently long until you reach a moment where, indeed, you have some kind of... Fine. Now, to control the solution up to some finite time, this is something which can be done by computer, because it's enough to have an approximative solution. You put it back in the equation, do some perturbative analysis, and because you have the small data theory, you can also do the small perturbations. So that, in principle, can be proven by a computer.
What particular data you start with? How do you prove with computers that true for any small data?
Well, you can go on, you can just cover, if you have a compact, that's why I said the classical data. So you would consider a set of classical data which form a bounded set and just cover by small balls and look at the error. So that, in principle, can be done. Of course, if you believe that there could be a breakdown of regularity, then that does not work. Now, at that stage, the situation is such as that we do not know. It's not that we don't have an existence theorem for large data, it's just that we don't know a single one. So, I mean...
analyze solution in a critical case are known not only in a radial case, but people did it numerically for some rotational.
Right.
Yeah.
Well, what I said in the beginning is that for the next century, what would be quite good is to have certified numerical experiments, so that we can really be sure that the people did what they were supposed to do. So that these experiments should be checked over again. Well, here it's not so bad, but when we're talking about blow-up behavior, then the situation really becomes rather wild. I have one transparency here, which I would perhaps leave for later. So the main thing here is some kind of a general, this is also a philosophical problem, is that you work very hard because you don't have enough conserved quantities or a priori bounds. So this is some kind of a general direction which is somewhere between the standard general analysis of PDEs on one hand, and then on the other hand you have things which have an enormous amount of structure, which are integrable equations, is just to understand how you can kind of get an insight in whether you should expect more a priori bounds, more conserved quantities or not. In a way, in this generality, you are stuck with H1. You don't go beyond H1, and this is why the theory is so difficult. Now, there are two possibilities. Either there is no more, and then the thing is indeed quite difficult, or there is something else, some kind of a priori bounds on higher conserved, some a priori bound on higher Sobolev norms, or some mechanisms, say, which are stronger than the standard dispersive scattering mechanisms, and then it would make the whole thing trivial. So it's certainly a question how you can do any kind of investigation on that.
Yes,
So,
one can show that there are no more local concerns.
yes, but they may be more complicated and equally good. For instance, something like a pseudo-conformal conservation law, something like that, which will involve the right signs, and this is not so clear. So in this field, there is some kind of, I wouldn't say a competition, but there is a melting of two types of inputs. One type of input is pure analysis, harmonic analysis. Then the other input is integration by parts, which is purely algebraic and not so easy to get an insight when you get the right signs and when you get the wrong signs. So there is quite a bit of experimentation possible there on the level of mathematics, if you want, which is a different kind of computer-implemented research. Bon, okay, now let me talk. Actually, I can leave that here. Let me talk about the other side of the world. So this was for defocusing. Now there is another thing, which is the focusing situation. So focusing situation, that's what they said, is that you expect to have blow-up phenomena as soon as the nonlinearity is sufficiently high. And if you want, on the first glance, it is not excluded simply because the Hamiltonian is not bounded from below and doesn't give any control on the H1 norm. Now, there are general mechanisms, at least for Schrödinger, there are general mechanisms to ensure that you will have such a blow-up behavior. But then the question is that people want to understand what are the fine features, whether there are some kind of universal features in the way these blow-ups look like. Fine. Now, the first question, so what they said is that the problem of the blow-up, for instance, is the fact that the H1 norm does not remain bounded. There is no contradiction because the Hamiltonian doesn't assert it. It doesn't control the H1 norm. So the question is, how fast do these H1 norms grow when the time goes to the blow-up time? So there is one situation which is quite important, which is that of the critical nonlinearity. Now, the critical here is not H1 critical, but really L2 critical. So this is the case that P is 2 plus 4 over D. So for instance, in dimension 1, P would be equal to 6, which would give me a 5th degree nonlinearity in the equation. In dimension 2, well, P would be 4, would give a cubic nonlinearity. Especially that one has been quite a bit studied. So in any case, what happens is that if P is less than that, you cannot have, for trivial reasons, you cannot have this blow-up phenomena. If P is 2 plus 4 over d or larger, you can have blow-ups for classical data. Now, what the blow-up means is that you will have a certain concentration. In that case, a p is 2 plus 4 over d. There is a concentration of L2 norm, and what is known, and this is not very difficult, is to show that the rate of blow-up is at least like 1 over the square root of t minus capital T minus small t, capital T being the time where this blow-up occurs. Now, you can say that this is kind of a very special problem which is not at all appropriate to discuss in this kind of a meeting, but the situation is such that this is an issue which has been quite a bit studied, a lot also on the numerical level, and it's certainly one of these topics. It's usually the case when people can't prove nothing, they start speculating a lot, and there is a lot of there are a lot of conflicting opinions of what is going on. So in any case, what one tries to understand is what is the exact rate. Now, one conjecture which definitely coexists with all the possible experiments or claims of a mathematical level is that this blow-up should be faster than 1 over square root capital T minus t. So it would certainly be quite nice to prove a result which is stronger than the one which is written down there, that not only this is bigger than a constant, but in fact that it will go to infinity, which is a statement which is made there. Now, one equation which has been numerically quite a bit studied is the critical equation in the two-dimensional case. And, well, I mean, there are various, say, what they call mathematical models, which are, for instance, based on scaling considerations and things like that, which will give you a growth rate which is faster than 1 over square root of t minus t by either power of a logarithm. In fact, these are supposedly unstable. Numerical experiments rather give the slower rate, which is as slow as a double logarithmic addition factor here in that growth rate. Now, maybe something recent happened, but say so far, what it looks like is that these things are definitely difficult to prove. And on a mathematical level, what certainly would be interesting is to get anything which is better than the trivial growth. Again, there is this issue of how reliable are the numerical experiments in this respect. Now, I will put on one transparency because it's closely related to what Jörg Fröhlich was talking about. There is one thing which is very mathematical, maybe not, well, I mean, exactly what one wants to study, but there is one thing which one can do, is to study what happens with the ground state. So what I denote here in this way is what is called a Town soliton, which gives you a ground state solution of that conformal equation. Now, that conformal equation has one more symmetry than in the equation Jörg was talking about, which was only involving Galilean symmetries, which is what is called the quasi-conformal symmetry. So there is an extra transformation which leaves that particular equation invariant. And, well, based on that transformation, it is possible, as you can see, to transform. So that transformation creates you another solution, which is written down below. And starting from this ground state, it's not difficult to see that what you get here is exactly is an explicit blow-up solution. It will blow up at time t equals 0. And the rate of blow-up in H1 is, in fact, not 1 over square root of t, but will be 1 over t there. Now, of course, I mean, it turns out that this is not a stable one. It's not a stable one simply because of the following, is that if you want to look at a blow-up solution, then necessarily you must have at least as much L2 mass as the L2 norm of Q, of this ground state. So if you start from an initial data which in L2 is smaller than the L2 norm of Q, you will not have blow-up. And moreover, one knows exactly if you have a blow-up solution which L2 norm is precisely the L2 norm of Q, what this blow-up solution will look like, and the only possibility basically is that behavior up to the natural symmetries of the equation. So if we are talking about an L2 norm, which is exactly the L2 norm of Q, then the blow-up situation is, say, completely understood. Now, there is quite an interesting question there, which is a question of quantization. What one believes is that it's not unreasonable that if you have any kind of blow-up phenomena, say for that equation, say take d equals 2, that necessarily what will go up in a single blow-up point needs to be an integer multiple of the L2 norm of Q. What can be constructed, of course, what can be constructed are solutions which are superpositions of a blow-up behavior like the one which is here and something which remains nice and will disperse at infinity, which on the level of the ground state is saying that, you can construct solutions which will be superpositions of the ground state solution and then something which will scatter at infinity. In fact, one would like there to have some kind of a general theorem, and we are close to being able to prove a general theorem. You cannot expect any kind of perturbative theorem because it's simply not stable. But it is stable within, it looks like, within a finite codimensional manifold. So you can, basically you have a finite codimensional manifold in a neighborhood of Q, so that if you take an initial data there, then the evolution will be the superposition of this ground state evolution, this down soliton, and something which is dispersive. This is very close to what Jörg Fröhlich was talking about. The difference here is that we are in a situation which is more critical than in his situation. The effect of it is that when you linearize the equation at Q, because of this extra conformal symmetry, you have something which has a bigger null space, which is more degenerate. So, of course, any kind of perturbative analysis has to go through the linearized equation, which is a non-Hamiltonian equation, and one needs to have a good understanding of what are the instabilities and so on. What makes this analysis possible is an important fact is that you do not have positive Lyapunov exponents. So the instabilities there are only polynomial instabilities, otherwise it would be quite hard to do any perturbative analysis. So this is some thing which I believe will be completed, and at least it will give you a certain class of explicit blow-up solutions. But it will not answer the general question whether the blow-up has to be necessarily always faster than 1 over the square root of t minus t. Now, how much time is left? 10, 15 minutes? More, 15. Okay, 15 minutes. Good. So now I will switch to something completely different, which is the situation of studying the equations on bounded domains. So if you have bounded domains, there is no room to disperse. This is clear. And what you are really after are other mechanisms than scattering things. Say on the level of experiments, it is clear here that you cannot expect to finish the proof simply by numerics, because it's kind of a mystery what is going to happen when t will go to infinity. It's not like that the evolution will be basically captured by linear evolution, because there is no place to have any kind of dispersion. So there are all kinds of problems and methods one can try to exploit, and of course in this setting it is quite tempting to consider ideas which are coming from the classical theory of dynamical systems, smooth dynamical systems, and try to push them in infinite dimensional phase space. And this is a source for quite good problems, in fact, which has not only enriched, say, if you want, that field on the PDE level, but has shed some new insights in, for instance, the construction of Km, of invariant Km tori in a purely classical setting. And I will try to give you a few of these ideas. Let me maybe postpone that. as I said, there is no scattering. If you have scattering, well, basically, it's the best possible evolution one can expect. Unfortunately, if you are on a bounded domain, the general dynamics is very, very difficult to track, except in one case, which is well understood, which is the integrable case. Unfortunately, again, is integrable, or fortunately, these integrable models are rather special equations, and they do not really shed too much light about dynamics for more generic equations. Still, if we consider an equation like the one which is written there, which is an equation with a smooth nonlinearity, we're trying to understand dynamics in phase space. So in 1D it is integrable. Say in 2, 3D it is not integrable, but it certainly remains quite a nice equation. Now, about existence of global solutions, there is absolutely no problem, and one can prove that there is a global existence for any data, any classical data in HS, or this is HS on the 2 or 3 dimensional HS on, say, the 2 or the 3 dimensional circle torus, as soon as S is at least equal to 1, so there is no problem. Now, the control on the H1 data, the control on the H1 norm is gotten from conservation of the Hamiltonian. There is an obvious problem, is what happens with higher Sobolev norms. If you have scattering, well, you will have uniform bounds in time. What you can prove, this is not totally obvious, but this can be done as a byproduct of the method, is to show that if we start from an HS data, at least we can get growths in time of these HS norms, which are at most power-like in time. What would be obvious is an exponential estimate, but you can get a polynomial estimate. You can get a power-like estimate. Now, I think what is certainly an important and challenging problem is whether there is any growth of these higher Sobolev norms at all. Of course, this is very much related to what I said in the beginning, is that you have a lack of conserved quantity, so there is a certain speculation there. What happens with higher Sobolev norms? Of course, if you have scattering, then you get out of you can solve the problem. But in this situation, there is not too much you can do. Now, what I would conjecture, I'm not sure I will put it really as a conjecture. Let's put it as a problem to be on the safe side. Is to have growths here which are at most like any small power of time for that particular equation. I think this is certainly a reasonable problem. Let me tell you that if, well, this is the analytic number theory notation. Yes? Right. Yes. So in any case, let me say you that this is one of the issues where the different dispersive behavior of the Schrödinger equation compared with the wave equation helps, because it's not so hard to make examples, say even in 1D, of nonlinear wave equations, say with the basically cubic nonlinearity, where you have a growth which is actually power-like. But in the case of the Schrödinger equation, it doesn't seem possible to make such a construction, simply because there are much better separations of these frequencies. I will come back on that on my next transparency.
You have your safety valve there. Do you actually have examples which actually...
Yeah, I have everything, but except what I want to have, of course. But there is one interesting fact. You see, when you try to simulate such a nonlinear equation, one thing you can do is decide on a certain evolution of u in time, and then replace u squared by a certain potential which is time dependent. So what is remarkable is that if I put here any, say, smooth bounded potentials which is periodic in x arbitrary dimension and smooth in time, but no behavior can look at periodic, quasi-periodic, or even a random behavior in time, as long as it remains smooth, then that thing is satisfied. You have these growth which are as slow as any power. And just to answer your question, you can make example even in the simplest possible cases where there is a logarithmic growth. So even with non-resonant incommensurable frequencies. So there is such a possible growth. Now what you would like to do is to use that fact as a first step to do some kind of nonlinear theory, but this is not so easy. So what I told you is that there is a difference here between wave equation and Schrödinger equation, and this will be even more important on my next transparencies, in the behavior of normal frequencies. What I wrote here is what I said before, is that for the wave equation there is a possible growth for things which are very close to the standard cubic wave equation. The point about the frequencies is that for Schrödinger you have frequencies which behave like n square. And for the wave equation they behave like absolute value n. N here should be thought about as an element of z at the power d, okay? Now, of course, the arithmetical properties of n square are much better than that of n, and there is much more separation there. I don't want to be precise in this. It's obvious in one dimension that there is much more separation in the squares than in n's, just integers itself. But there is such an effect also in higher dimension, which will make it very difficult in a model, in a linear model like that one, for instance, for this energy to move from low to high mode, simply because there are very strong separation, arithmetical separation properties, which you do not have for the wave equation. So if you want, what lies behind that are effects which are very much related to localization of eigenfunctions with quasi-periodic potential for lattice Schrödinger operators. Now that is also, I guess I probably don't have more than 5 minutes left. So I have to make a choice now. Let me talk about KM theory, since I mentioned this. Okay, so I leave that one. You see, as I said, there are very little explicit solutions known if you are in global solutions known, if you are in non-integrable settings. And one way to construct these explicit solutions is by using KM theory. So you basically construct KM tori the same way as you construct KM tori in classical mechanics. The big question which is there, of course, you do not expect that the whole phase space is filled with KM tori. So the general question is to understand how much of this KM tori you have there. Well, the case of one-dimensional tori, this is simply time-periodic solutions. The finite dimensional tori correspond on the PDE level to quasi-periodic solutions where you have a finite number of frequencies, and infinite dimensional tori to almost periodic solutions. There has always been some concern in KM to develop an infinite dimensional KM theory. Now, there are two things. Here the phase space is definitely infinite dimensional, but the tori may be either finite or infinite dimensional. In any case, infinite dimensional tori in this setting, they have a very natural appearance because it's just the situation of almost periodic solutions. For instance, if you have a KdV, right, which is an integrable equation, then you know that all solutions will be almost periodic. But this is not going to be the case for a generic equation. Still, one can construct in a rather large generality certain almost periodic solutions, which are infinite dimensional tori in your phase space, which in fact can involve all frequencies of the system, which can be infinite dimensional tori on a full system of frequencies. The question is how big are these tori and how much of these tori do you have? Now, the difficulties is that we have resonance problems, which are new resonance problems due to the fact that the phase space is infinite dimensional. So even in the case of one-dimensional tori, which in the classical setting would not involve small divisors, in the case, say, of 1D wave equation, they will involve small divisors because of an infinite dimensional phase space. So what was necessary is to develop a certain KM type scheme which permits to treat resonant problems which are, well, natural in this context, and certainly become, these resonances become quite severe in space dimension d and larger. Why in space dimension d and larger? Well, what I said is that you have these normal frequencies which are like n square. For instance, for the Schrödinger equation, it's clear that if you fix n square in 2 dimensions, then you get lattice points on a circle or in higher dimension on a sphere, and you have quite a bit of them. So that kind of multiplicities is not acceptable with the most standard KM scheme. And so there are new methods. These new methods are actually quite related, say the additions to the method, let's put it like that, are quite related to research that has been done basically in the 80s around perturbative localization with lattice Schrödinger operators and quasi-periodic potential. And say on the purely conceptual level, even in a classical setting, it has enriched the theory because what it allows to do, for instance, is to construct invariant tora with positive Lyapunov exponents, which you will have positive Lyapunov exponents if you have multiplicities in the normal frequencies, and that is something which was ruled out by the at least by the classical scheme, like was alluded to in Yesh's nice talk. So in any case, let me conclude with two problems here. What has been well developed at this stage is the theory of one-dimensional tori in arbitrary dimension. Now for quasi-periodic arbitrary space dimension, so for quasi-periodic solutions, what is reasonably well developed is the one space dimensional setting. Of course, when you go in higher space dimension, you will have stronger multiplicities in these normal frequencies. So the only model at that stage which is really fully understood, well, not quite fully understood, but to some extent understood, is the Schrödinger case in 2 dimensions. For the wave equation, it is not known. Almost periodic solutions corresponding to infinite dimensional tori. Well, what is really the idea there? It's not at all clear that when epsilon goes to 0 in the perturbation of your Hamiltonian, of your integrable system, you will have, say if the dimension of the phase space and the dimension of the tori goes to infinity, it's not at all clear that the epsilon in the perturbation will be possible to keep it away from 0. So the trade-off which is going on there is that you basically look at the action variables of the system and you let them go very rapidly to 0. So it is true that these almost periodic solutions, they live on a full set of frequencies. Frequencies which are not that great because they don't grow exponentially, so you have quite a bit of Diophantine small divisor problems there. But the trade-off is that you have these action variables which go very rapidly to 0. Nevertheless, even if you're allowed to have these action variables going as rapidly to 0 as you want, it's still not clear that you can do that. And I think what is a natural problem there is to find some realistic decays, like perhaps real analytic or something. Real analytic may be something too much to ask, which of course has to do with understanding the abundance of this invariant tora in the phase space. So I believe I will stop here. I'm only 5 minutes over.